Welcome to this MedChemica MC Pairs online training video. In this video, we'll describe the science behind matched molecular pair analysis, and we'll use a real project example to illustrate the process. Watching this video provides the background and understanding that underpins the exploitation tools included in MC Pairs. These are rule design, spot design, compound to pairs, and the MyPairs system. To start with, why do we use matched molecular pair analysis? Imagine we're in a drug discovery project where the key questions are: what is the next compound we're going to make, where do we get our inspiration, and where do we get a diverse set of good ideas? Well, if we analyse the data from older projects, we can build a knowledge database of what worked and what didn't work in the past. If we apply that learning to our current projects, we can avoid pitfalls, dead ends, and focus on the chemical changes most likely to yield superior molecules. We can have confidence in these ideas because we can link back to the compounds and data and see what happened in the past projects. More importantly, we can get new ideas we would not have thought of. Overall progress in our current project is accelerated, and costs are reduced in both lead identification and lead optimization. This can accelerate overall progress in our current projects and reduce costs in both phases. In this training video, we'll use the discovery of an AKT inhibitor, AZD5363, as a project example. Here's the reference if you wish to read the paper. In summary, the lead optimization phase started with a good lead, Campbell 598194, but this fell short due to unreliable crystalline solubility and a poor margin in hERG inhibition. At MedChemica, we talk in changes between compounds and work on a logarithmic scale for our analysis, so you'll see these delta values between pairs of compounds. Small improvements were made with a chiral methyl group with a half log unit improvement in solubility. The project had structural information and found room to extend out a group with this methylene position. The team tried basic groups that did improve solubility without affecting inhibition. However, all bioavailability was lost and clearance was higher with Campbell 2325729. Trying many other polar groups, the team found that a simple alcohol gave the candidate drug. This group improved solubility, pushed out hERG inhibition, reduced lipophilicity, and increased potency. It's remarkable that we can often summarise a project in just 4 compounds on a slide. Had the project team known that this alcohol side chain would improve several properties, they could have prioritised this for synthesis. From the early compound, the extension of CH2OH is the transformation that led to the candidate drug. Let us consider this transformation of CH2OH. Here we have the match pair from the project. The molecules are exactly the same apart from the methyl group and the CH2CH2OH. The change creates 1 log unit improvement in solubility between the measured values. On the second row, consider this match pair. The structures are very different from our AKT compounds. The difference between the compounds, the transformation, is again an extension of CH2OH. With this pair, the difference is 2.3 log units. And here is a third match pair. Again, it's a diverse scaffold, but the same difference of CH2OH. In this case, the measured solubility difference is 1.6 log units. So we have 3 match pairs where the change is CH2OH and it improves solubility. If we use this transformation on our current series, we can have high confidence that it's going to work. The median change is 1.6 log units. If we make a new compound with this transformation, it should have a significant improvement. So, the matched molecular pair method finds all the match pairs for all the compounds and finds their differences in solubility using measured data from these pairs. We group the pairs together on transformation and then perform statistical analysis on the delta measurements. If we have 6 match pairs where the same transformation has improved solubility, then there's a 95% confidence that transformation will work on your future project. So, on a larger scale, we catalogue all of the publicly available chemical transformations, or for our enterprise customers, the transformations from their internal company datasets and store them on a database. We can then perform our match pair statistical analysis across a range of assays. Here's a sample for the transformation of the CH2OH extension from our database. There are 69 match pairs with this transformation, and 47 of them improve solubility, while 21 don't. This still passes a statistical binomial test. The median change is 0.26 log units, so half the time the improvement is larger than that. The standard deviation is 0.636, giving us an idea of how the data is spread across the set of pairs. So you can imagine the shape of the signal in your head and get a feel for how likely this transformation will help your project and how big the change will be. You're probably wondering why we don't report the mean. For the most part, the transformations have 6, 7 or 8 matched pairs. If one of these values is erroneous, then it could pull the mean value one way or another, giving a false impression. Therefore, we report the median, as it's a true measured value. Similarly, you may have noticed that 47 plus 21 doesn't equal 69. We found 69 chemical matched pairs, where both values had measured solubility, but we only consider pairs where at least one of the measured values is on scale. So in other words, one pair here has measured values that are both out of range of the assay. Having examined all the matched pairs for the CH2OH extension, we can say that we have a rule for improving solubility, where a rule is a statistically significant chemical transformation. Here's the decision tree for labelling transformations as rules. There are 4 labels: increase, decrease, neutral, and ned, where ned stands for no effect determined. The cartoon on the left shows the hypothetical shapes that a distribution of delta values can take for a set of matched pairs. For several ADMET properties like metabolism, efflux ratio, clearance, and hERG inhibition, the decrease direction is desirable when optimizing an orally bioavailable drug. We often want to decrease metabolism. This is how we speak as compound designers. If all the matched pairs for a transformation have similar values, a tight distribution is yielded, and if the distribution is located in the negative range, then we have a perfect decrease rule. If we reverse the matched pairs so that the chemical transformation is going in the opposite direction, the delta values are flipped, and we have the mirror image of the distribution in the positive range, making an increase rule. So our previous CH2OH example of increased solubility was a positive distribution. There are chemical transformations that reliably make no difference to a measured property, and we call these neutral rules. They have a distribution with a median very close to 0 and a tight intercentile range of 0.3. The last label is no effect determined. This is where we have more than 6 matched pairs but they fail the statistical test, so we cannot assign increase or decrease. However, we still capture and present the statistical significance found with the test. For example, we could have 20 matched pairs but only 14 are positive. This is not a 95% confidence, but in medicinal chemistry, 14 out of 20 is not bad. We still capture this data as it can be useful in decision making. We'll cover how to look at NED data to make judgments on compound suggestions in a later video. If you'd like to read further on the rule finding process, here is the reference that describes the full decision workflow. In short, the process of matched molecular pair analysis uses high-performance computing to find all the chemical transformations in large datasets and simply counts how many times they work to improve properties. Statistical analysis tells us the best and most reliable transformations to apply in future projects. If we think about it, this is basic medicinal chemistry. We see an example of a transformation in the literature, at a conference or from internal projects, and we use that knowledge in our current projects to improve compound properties. Having built this database, how does MC Pairs use this knowledge? Here's a schema of the tools available in MC Pairs. Here is the database of compounds and data from an organisation that has been loaded up, cleaned and organised ready for analysis. We use high-performance computing to find all the matched pairs. The rule finder that we just described is applied to yield a database of exploitable knowledge. The rule design engine can then process a user-inputted problem molecule and generate new ideas by applying the relevant rules from the database to mutate the compound. The statistical data is supplied with each compound suggestion for the user to explore. These data provide real-world evidence on which to base decision-making for progressing compounds through your synthesis and testing cascade, which is especially useful if the synthesis is complex. Of course, as chemists you'll have your own ideas. Use the spot design engine to enter your problem molecule along with your new idea molecule, and it will query the knowledge database for evidence to support your suggestion. As with rule design, the statistical data and match pairs are supplied. Compound to pairs is a tool that outputs all of the match pairs present on the database for an input molecule. It also supplies the measured data along with the common cause and R groups so that you can explore the structure-activity relationships. Rule design, spot design, and compound to pairs are covered in additional software training videos. Additional MC pairs tools are available. The MyPairs suite allows the user to upload and process their own file of compounds to generate match pairs and rules, and a process called permutative match molecular pair analysis, which can transfer all the SAR between compounds in series and show the molecules that have not been made. With the clean data ready for analysis, we can also generate machine learning models to predict binding affinity of compounds to protein targets. This too is covered in another training video. Thank you for watching this training video. We hope you find it useful. For further support, please contact support@medchemica.com.